All right, so this short video is actually in addition to this unit. Dalton's law of partial pressures is sometimes a sticky point in this unit, so maybe having this as a backup video for some extra help hopefully will help. So Dalton is somebody you've heard about before. He is the same guy that we've heard about in his atomic theory and that we've talked quite a bit about. But he also liked to play around with a lot of mixtures of gases and make a lot of observations and experiments about that. So rather than study, like a lot of the other people that we've talked about, rather than study a single gas at a time, he would actually study a mixture of gases. So he would mix, say, hydrogen, helium, and oxygen all in one container, and what he found is the total pressure of the container actually was the sum of all the pressures of the individual gases. So the pressure of the helium and the pressure of the hydrogen, the pressure of the oxygen, all added up and equaled the total pressure of the container. Now this seems pretty simple, and you oftentimes see it in textbooks as in the total pressure is equal to the pressure of the one gas plus the pressure of the second gas and third and so forth, however many gases you have in the container. And then we kind of combine this idea with the ideal gas law, and we get something like this, as in P equals nRT over V. Hopefully you can see that kind of rearrangement then. But what he found was it wasn't just about the total pressure, it was more about the total moles, the fact that he could add up the moles of the hydrogen, the moles of the helium, the moles of the oxygen all together, get the total moles, and then that was representative of the total pressure in the PV-nRT equation. So this is what this is all boiling down to, and I thought the book had a pretty good diagram about this. So if I have 4 moles of a gas, that's what these little dots here represent. If I have 4 moles of a gas, I have a little bit of pressure. And if I have 10 moles of this red gas, then I have a little bit more pressure. And then when I combine the two, so I have 4 moles of the blue, 10 moles of the red, I have a combination of this pressure plus this pressure up here, okay, which is what we just talked about. So if 4 out of the 14 moles belong to the blue gas, then 4 out of the 14 fraction of the pressure also belongs to the blue gas. So the idea is if I know what percentage of moles that I have, then I automatically know what percentage of the pressure belongs to that specific gas. Hopefully that made sense. So Dalton's law of partial pressures, those concepts we see kind of repeated in quite a bit of the problems over and over again. So the example problem number 15 you can find in the book here is page 199 is the beginning of Dalton's law of partial pressures, and obviously I encourage you to take a look at it. Here's that little diagram I just explained. Example problem 15 is on page 200, and hopefully you've also seen how it kind of breaks all this down on strategy and so forth. So I use these problems on purpose because I think they're very well spelled out in the book and a good reference, so it's good to kind of mirror that stuff in class. So anyway, this problem, mixtures of helium and oxygen can be used in a scuba diving tank to help prevent the bends, which is a good thing. You don't want to get any of that. For a particular dive, 46 liters of helium at 25 degrees in 1 atmosphere and 12 liters of oxygen at 25 degrees in 1 atmosphere are pumped into one 5-liter tank. So that's a lot of gas. 46 liters, 12 liters, all pumped into 5 liters. Calculate the partial pressure of each gas and the total pressure of the tank at 25 degrees. So we have a couple different things here. If you look real close here at the helium, I have 46 liters of helium at 25 degrees in 1 atmosphere. That's enough information right there to use PV-nRT and get moles of helium. And again, same idea here, 12 liters of oxygen at 25 degrees in 1 atmosphere, I can get moles of just oxygen. Okay, so that said, if I plug this into PV-nRT for the helium, I'm going to get 1.88 moles of helium. Okay, And if I plug this one in to PVNRT, I'm going to get 0.49 moles of oxygen. Okay. Now I'm taking these moles, 1.88, and the 0.49 moles into 5 liters at 25 degrees. Now I can also use PVNRT again, and this time solve for the total pressure. Now there's a couple different ways you can do this. So obviously I can use PVNRT. I can put my total moles in for the N, use my 5 liters for the volume, and get the total pressure. And then I can find out what percentage of moles is helium, and then take that percentage of the total pressure to figure out partial pressures. Or I can do PVNRT for just helium. Okay, I can put just helium in there, get an answer for the pressure. And if you do that, this would also be at 5 liters, I would get 9.3 atmospheres. Okay, and then I'm actually not going to put an equal sign. Let's put that. And then if I put in just my moles for oxygen, okay, then I would find out that 2.4 atmospheres of the total pressure belongs to oxygen. To get the total pressure in the tank, I would just add this and get a total of 11.7 atmospheres. Okay, again, there's a couple different ways you can do this. You can find the percentage of moles, put in your total moles into PVNRT here, then get your percentage of pressure, or find your individuals and just add them up. Okay. So mole fraction, and I know you've seen this before because we just talked about this in Unit 4, but mole fraction comes into play because we're really talking about what percentage of moles belong to a specific gas out of a total mixture. So if 50% of the moles belong to oxygen, let's say, then 50% of the pressure belong to oxygen. So we've got a direct relationship there. So here's another example of another Dalton's law problem. The partial pressure of oxygen was observed to be 156 torr in air and a total atmospheric pressure of 743 torr. Calculate the mole fraction of O2. So again, if this much pressure out of the 743 is just oxygen, then that's not only the percentage, so I'm going to take this torr divided by 743 torr. That's not only the percentage of my pressure, which if I do that, I'm going to get a little more than 25 or 20%, okay? But that's also the percentage of moles in there. And if I want mole fraction, rather than change it into percentage, I'm going to just round this to the right number of sig figs there. And then there's my mole fraction, because 0.21 is the mole fraction, since that's the percentage of the pressure, that's also the percentage of the moles. All right, another one, again, along the same lines. The mole fraction of nitrogen in the air is 0.7808, or about 78% of the moles in the atmosphere belong to nitrogen. Calculate the partial pressure of nitrogen in the air when the atmospheric pressure is 760. Okay, again, if the total is 760 torr and 78% of the moles are nitrogen, then I'm going to just take my mole fraction, okay, or my percentage of pressure, and multiply the two, and I'm going to get 593 torr. Okay, hopefully pretty straightforward. All right, the other place where Dalton's law of partial pressure applies is when we're collecting a gas from an experiment over water, which is very common. When I'm trying to isolate the gas that might be coming out of an experiment, so like I'm heating this stuff right here, and I'm trying to isolate what is coming off of it, I'm going to do that through water, so I'm isolating just what's coming off of this. The only thing is when I do this, I'm not isolating just the oxygen that's being pumped off this experiment, I actually have a little bit of water vapor also. Hopefully you're aware, I know we've talked about it a little bit, but water vapor is in the air all the time. And so just the fact that I've isolated this didn't remove that. In fact, the fact that I collected this over water ensures that I have water vapor in that section. So anytime I do that, I have to make sure that that water vapor is subtracted out so I know the pressure of just the oxygen in this section. Okay, so it's normally just, with these problems, is just recognizing that there's water vapor in there and taking it from the total pressure. Okay, so if I can figure out the volume of the gas that's being collected, if I can figure out the pressure that's involved in there by subtracting out the water, I can get moles because I would know temperature, and then I could actually work backward with some stoichiometry and figure out the moles or maybe even the mass of what I started with. Okay, so vapor pressure of water in these type of problems are usually given. You just have to recognize that it's there and subtract it out, just like this problem here. So if I have a solid sample of potassium chlorate here and I'm heating it in a test tube, and as I'm heating it, I'm actually making it break apart in this formula right here, in this reaction. So my two products are this solid right here and then this oxygen gas. So I'm heating it up, it's producing this oxygen which is going down this tube, and I'm collecting it into this container so I can actually measure it. Okay. So when the oxygen is produced, we collect it at 22 degrees. The total pressure is 754. The volume of gas, so it's measured, the volume that we collected, and then it tells us the vapor pressure of the water at 22 degrees is 21 torr. Now, water vapor is constant at particular temperatures. So it's given in charts, it's given in books. All you have to do is know what temperature it is that you're running the experiment, and then you can find automatically what the vapor pressure would be at that temperature. So when we look at the pressure of oxygen, we need to take that 754 and subtract the 21 from it, and then we know the pressure of just the oxygen. Okay, so the rest of this problem talks about calculating the partial pressure of oxygen, which we just talked about, subtract the two, and also figure out what the mass of the sample was that originally decomposed. So if you imagine, if I know down here in the equation, if I know the volume of the oxygen, I know the pressure once I subtract those two, and I know the temperature, I can find moles of this oxygen. Once I find moles, I can mole ratio into the potassium chlorate and then eventually go to mass. So that's the strategy of this kind of problem. Again, total pressure is 754. I'm going to subtract the 21 from it. And then once I find the moles of the oxygen, I mole ratio into the potassium chlorate and get the mass. So hopefully I would suggest that you pause this, or at least take a look at the book, make sure that you understand that process, and hopefully you get 2.59 times 10 to the negative second moles of oxygen, which would then mole ratio into the potassium chlorate and get a mass of 2.12. All right, while some of these problems can get a little bit complicated, just try and come back to your basics in terms of adding up the pressures for the total and adding up the moles for the total and using your mole fractions. Okay, hopefully you find this helpful, and see you in class. Have a good night.